Welcome to this HP Expert 1 presentation. This is the second video discussing spanning tree. In the first video, we looked at the basics of 802.1d or common spanning tree. I also introduced some other basic concepts with regards to spanning tree. Now let's scale the topology and look at a more real-world example. In this topology, we have two core switches, switch 1 and switch 2, and three access switches, switch 3, switch 4, and switch 5. Let's assume that the customer is running 802.1d, in other words, common spanning tree, and let's assume that no priorities have been set on any of the switches. In other words, the default priority of 32768 is being used by all devices. For simplicity, let's assume that the MAC addresses are as follows: A, B, C, D, and E. Now hopefully you can see that immediately there's a problem in this topology. With spanning tree, the first decision is to determine who the root bridge is or root switch. If the priorities are the same, which they are in this example, then the determination of root bridge is done by MAC address. The device with the lowest MAC address will become the root bridge or root switch. The core switch in this topology will thus be A. An access switch became the root bridge or root switch in this topology. Now be careful. Lowest MAC address wins. In other words, older switches are more likely to become the spanning tree root than new switches. One of the big mistakes that network engineers make is they deploy switches, enable spanning tree, but don't optimize spanning tree. And this is what happens. Your oldest switch becomes the root of your topology. So let's see how that affects the flow of traffic. Once we've determined the root bridge, the second step is to determine root ports. So every switch that's not the root of the topology will determine a single root port, which is its best port to get back to the root bridge. So on switch 1, the root port is port 1. On switch 2, the root port is port 1. What about switch 4? It has two options. It can either use port 1 or port 2 to get to the root. Looking at path costs, which is the first criteria when determining root ports, if the switch took this path, the cost would be the same as this path. So there's no difference in the path cost. So that can't be used as the determining factor. The next decision is neighbor bridge ID. In other words, what's the lowest bridge ID of a neighbor? In this case, D is lower than E. Thus the path via D will be used. So the root port on switch B will be port 1. What about switch 5 with MAC address C? Its root port will also be port 1 because the bridge ID of switch 1 is lower than the bridge ID of switch 2. In other words, MAC address D is lower than MAC address E. So at this point, the root switch has been determined. Switch 3 is the root because it has the lowest MAC address. Root ports on every other switch have been chosen. So on switch 1, switch 2, switch 4, and switch 5, there's a single root port per switch. The next decision is to choose designated ports. Designated ports are chosen on a per segment basis. Once again, using the analogy that if I was at the center of this cable, which way would be the best way to get to the root bridge? Would I go to port 1 on switch 3 or port 1 on switch 1? Which is the shortest path? And I think it's quite obvious that that is a shorter path than trying to do something like that. So, the designated port on this segment is port 1. What about this cable here? The designated port here would be port 2 on switch 3. Essentially, all ports on the root switch are designated ports. You can't get closer to the root switch than the root switch itself. What about this cable at the top? Do we go left or do we go right? The costs are the same. 10 gig interface here, gig interfaces over here. Once again, D is lower than E, so the bridge ID is lower. So switch 1 would have the designated port on that segment. Now continuing, this port is the designated port on this segment. This port is the designated port on this segment. This port is the designated port, and this port is the designated port on their segments. Just look at the path cost or neighbor bridge ID to determine the shortest path. In other words, if I was in the middle of this cable, it's quicker to go there than it is to do that. So this would be the designated port rather than this port down here. Once designated ports have been chosen on a per segment basis, all other ports are put in the blocking state. So this port is blocking, this port is blocking, and this port is blocking. Spanning tree has removed loops from this topology. So this is what the physical topology looks like. However, logically, this port is blocking, this port is blocking, and this port is blocking. Having a look at our spanning tree topology, the 10 gig interface on switch 2 is blocking, this gigabit interface is blocking, and this gigabit interface is blocking. So when someone looks at the physical topology, it looks good. We have 10 gig links between our core switches. We have gig links between the access layer and the distribution layer. But in reality, this link is not used at all. Only a few traffic types, such as LLDP and BPDUs, are sent through a blocking port. So other traffic is blocked. These links are not used for normal user traffic. Now imagine that there was a server connected to switch 2. So let's say this was a VMware server or some other server that users need to access. Let's assume that PC5 and PC6 need to send large amounts of data to that server and receive large amounts of data from that server. How does traffic flow? So PC5 will send traffic to its switch. This switch will send traffic to switch 1, to switch 3, which is the root of the topology, which will then send it to switch 2 and onto the VMware server. I'm sure you'll agree that this is not very efficient. Imagine that your core switches are very large switches, 7500 switches or something very, very big. And this switch on the edge is a 2610 switch. All traffic has to go through the root to get to that VMware server. The same applies for PC6 traffic. Gets sent to the switch and then has to go all the way around to get to the VMware server. This 10 gig link is not used for data transmission. By the same token, traffic from the VMware server needs to go via the root to get to the user machines. The same principle applies to traffic going to PC3 and PC4. All that traffic is going to traverse the root switch, which is a small switch on the edge of your network. So once again, physically the network looks good, but because of spanning tree blocking these ports, the throughput on your network may be very poor. A 10 gig link was blocked by spanning tree, and traffic needs to traverse 1 gig links rather than traversing this 10 gig link. So as I'm sure you'll agree, this is not ideal. So how do we rectify this issue with spanning tree? How do we optimize the network? So the first step with any variant of spanning tree is to set the priority of your root switches. Make sure that you lower the priority of the switches that you want to become root. Remember, the election criteria is based firstly on priority, and if the priorities are the same, then lowest MAC address. So first step, lower the priorities of your root switches. So the first step is to determine which switch is going to be the root. In this case, switch 1 will be configured as the root, and we'll lower the switch priority to 4096. Default priority once again is 32768, so we've lowered this to 4096. You could make it 0 if you prefer, but I'm going to use multiples of 4096 in these examples. So the first decision in spanning tree is to elect the root bridge. Switch 1 will become the root because it has the lowest priority. Even if the MAC addresses are A, B, C, D, and E, as per our previous example, switch 1 will still become the root because priority takes precedence over MAC address. The next decision is to choose root ports. So on switch 3, root port will be port 1. The same on switch 4, same on switch 5. That is the best port to use to get to the root switch. On switch 2, MAC address E, the 10 gig port is the best port to use to get to the root bridge. The next decision is to choose designated ports. All ports on the root bridge will be designated ports. So all of these ports will become designated ports. You cannot get closer to the root bridge than the root bridge itself. Now, best practice would say, change the priority of your other core switch to 8192 or a number that's lower than the default priority. We want to ensure that switch 2 becomes the root if switch 1 fails. So once again, you could have made the priority of switch 1 0 and switch 2 4096, but in this example, I've used 4096 as the priority of switch 1 and 8192 as the priority of switch 2. So because switch 2 has a lower priority than switch 3, on this link here, the decision for designated port would be to use switch 2 as the designated port on that segment rather than switch 3. So this will become the designated port. The same occurs on the other interfaces, designated port, designated port. So now that each segment has a designated port, all remaining interfaces are set to blocking. So this interface goes blocking, this interface goes blocking, and this interface goes blocking. One of the things that you'll notice is that this is a lot more deterministic than our previous example. In this scenario, the ports on the left are root ports, and ports on the right are blocking ports on all the access switches. Notice root port, blocking port, root port, blocking port. A lot more deterministic than this example, where on the first access switch we had 2 designated ports, and then root ports and blocking ports on the other access switches. This is also a lot better. The 10 gig link is not blocking. It can be used to forward traffic. So once again, here's our physical topology. The ports that are blocking are port 2 on switch 3, port 2 on switch 4, and port 2 on switch 5. Once again, we work that out by selecting root switch, root ports, designated ports, and then the blocking ports. So let's look at traffic flow. Is it better than our previous example? If we had a server connected to switch 2, would traffic flow better than the previous example? So PC5 and PC6 are sending lots of traffic to that server. Their traffic will now flow via the root switch to the server. In other words, that's a lot better than what we had previously. This interface is not going to be a bottleneck because it's a 10 gig interface. In a lot of networks, you'll see that multiple links are bonded here using link aggregation, also known as bridge aggregation. On Cisco, known as Ether channel. On switches running the provision operating system, it's known as a trunk. But essentially, we're taking multiple links and bonding them together so that this does not become a bottleneck when traffic is sent from multiple access switches to the server. So once again, traffic will flow like this to the server. So it's not ideal, but it's a lot better than we had previously. Traffic is traversing the core link between the 2 core switches. The core switches are more powerful switches than the access switches, so this is a lot better than we had before. So this is an example of 802.1d optimized in a LAN topology. The lesson to be learned is make sure that your core switches have priorities set that are lower than your access switches. Default priority 32768. Make sure that the core switch's priority is lower than that. However, this is not ideal. These uplinks are not used at all with 802.1d. traffic is going via the root switch to the server. Now you may argue, why don't you just make this switch the root? And that would work well in this situation where the server is on the right hand side. Traffic would then traverse across port 2 directly to the server. But if you had a server connected to this core switch, traffic would have to go via switch 2 to that server. Not all uplinks are used. So going back to this diagram, notice these links are not used at all. Only protocols such as LLDP and BPDUs are forwarded and received through a blocking port. So how can we improve this? So another version of spanning tree, per VLAN spanning tree, helped improve the utilization of links by allowing for the configuration of a root switch on a per VLAN basis. This was originally developed by Cisco, and there are two versions, PVST and PVST+. PVST was only supported on ISL links, in other words, Cisco proprietary trunk ports. PVST Plus supports ISL and 802.1q. PVST Plus is supported on HP devices running the Comware operating system as well as the Provision operating system. However, ISL is not supported because it's Cisco proprietary. So, in 802.1d, we could only configure a single spanning tree root. In PVST, we configure a spanning tree root per VLAN. So as an example, if PC1 was in VLAN 10, 2 in VLAN 20, and so forth and so on, so devices are in different VLANs, what we could do is make switch 1 the root for odd VLANs. So in other words, it would be the root for VLAN 1, the management VLAN, VLAN 10, VLAN 30, and VLAN 50. Switch 2 would be the root for even VLANs. So for VLAN 20, VLAN 40, and VLAN 60. It's important to note that in this topology, we have 7 VLANs. Our 6 VLANs for our users and the management VLAN. That means that there are 7 spanning tree roots. Switch 1 is the root for 4 VLANs. Switch 2 is the root for 3 VLANs. There are also 7 spanning tree instances. 1 instance per VLAN. So there's a lot more overhead in this configuration than there was in 802.1d. However, there are advantages with regards to link utilization. For example, this PC is in VLAN 10 and this PC is in VLAN 20. Switch 1 is the root for VLAN 10. That means this would be the root port on switch 3. Very much the same as what we saw previously with 802.1d. Root ports would be determined as follows on the other switches. We would have our designated ports on each segment. And once again, you would make this switch have a priority of 4096 and this switch a priority of 8192 on VLAN 10. All other ports would go blocking. So this port would be blocking, this port would be blocking, and this port would be blocking. So that would be the topology for VLAN 10. Traffic would go from the access layer to the core layer using port 1 on switch 3. The same would apply for VLAN 30 and VLAN 50. Traffic would traverse these uplinks. However, just note that the physical topology consists of 5 switches only. But what we've done here is we've made this switch the root for VLAN 20 and the other even VLANs. So in that case, this port is the root port on switch 3. Port 2 is the root port on switch 4. Port 2 is the root port on switch 5, and this is the root port on switch 1. We would make this switch have a priority of 4096 for VLAN 20, and this switch have a priority of 8192 for VLAN 20. Note please, that's the opposite of what we did with VLAN 10. Switch 1 had a priority of 4096 and switch 2 had a priority of 8192. That's been flipped round for VLAN 20. Designated ports would now be determined as follows. Blocking ports would be determined as follows. Notice please, on switch 3, the blocking port for VLAN 20 is on port 1. That means traffic from VLAN 20 will traverse this uplink. The same will apply for VLAN 40. Traffic will use port 2. The same for VLAN 60. So once again, just note that there are only 5 switches in this topology. However, because of per VLAN spanning tree, some traffic will traverse port 1 on the access switches, as per this example, and some traffic will traverse port 2 on the access layer switches. So unlike with 802.1d, where these links were not utilized, in PVST, traffic traverses both uplinks. So we get better utilization of our network. So that's a major advantage with per VLAN spanning tree over 802.1d. There are, however, once again, disadvantages with PVST. In this topology, we have 7 root switches, 7 instances. If that was scaled, and let's exaggerate a little, and assume we had 500 VLANs, in that case, there would be 500 root switches. There would be 500 instances. On every link, that's a trunk link. So let's say, for example, on gigabit 101, if 500 VLANs were permitted on that trunk, 500 BPDUs would be sent out of that port every 2 seconds. So 500 BPDUs on a per port basis. That's a lot of overhead. Now remember, there are only 5 switches in this topology, but switch 1 is going to be the route for the odd VLANs, and switch 2 is going to be the route for the even VLANs. There are 500 VLANs, so switch 1 is going to be the route for 250 VLANs, and switch 2 is going to be the route for 250 VLANs. That's a lot of overhead for a small topology. Another disadvantage of PVST is time. In the same way as 802.1d, PVST used timers to determine if a port should be forwarding or blocking. So ports went from the blocking state to the listening state to the learning state, and then if there were no loops, they went to the forwarding state. The problem here is that this would take 20 seconds, this would take 15 seconds, and this would take 15 seconds. You could reduce timers, but it wasn't recommended because you may have introduced loops. The whole idea with spanning tree is to reduce loops. And if your timers are too short, you may inadvertently introduce a loop. The difference between the listening state and learning state is that in the listening state, the switches are not updating their MAC address tables. In the learning state, they are. But as you can see, it could take up to 50 seconds for spanning tree to reconverge. Normally, if the switches are already booted up, they would go straight from listening to learning to forwarding. So it would take plus or minus 30 seconds for spanning tree to converge. That's a long time. If, for example, this was the root port of the switch and this port was blocking, and let's say that port went down, it could take 30 seconds before traffic traverses across the alternate port. Or if the root switch went down, it could take 30 seconds for the spanning tree topology to reconverge. That's not ideal, especially when you're using technologies such as voice over IP and other time-critical applications, which are often used today. Now, to try and increase performance, some extensions were made to PVST. One of those extensions is port FOST. In port FOST, the idea is that we have quicker or faster convergence on ports connected to end devices. So on these interfaces connected to PCs, you would enable port FOST. That's a Cisco term. The industry standard term is edge ports. On an edge port, the port goes immediately from the blocking to forwarding state. The idea is edge ports only have edge devices, such as PCs and servers connected to them. A loop will not take place here because we have edge devices connected to the switch rather than a hub or another switch. So edge ports would only be configured on interfaces where you have edge devices such as PCs or servers. The advantage here is very quick convergence. The ports immediately go forwarding. Another extension to PVST is uplink FOST. The idea here was, if this was the root port of a switch and this was the blocking port, if the root port went down, the blocking port would start forwarding a lot quicker than what you would have with traditional spanning tree. So rather than taking 30 seconds, much quicker convergence would take place. So within 2 seconds, that port would start forwarding rather than taking 30 seconds. Now these are proprietary mechanisms. There is another one known as backbone FOST, which we won't talk about here. But the idea was to increase the speed of PVST. Those enhancements were taken and rolled into a protocol called Rapid Spanning Tree. In Rapid Spanning Tree, you do not configure uplink FOST or backbone FOST, but you still configure edge ports. So the ports where users are connected would be configured as edge ports. Rapid Spanning Tree also increases the speed of convergence using messages between the switches rather than timers. So previously, ports would go through blocking, listening, learning, and forwarding states, which would take a lot of time. With Rapid Spanning Tree, timers are not used. Extensions to the BPDUs are used to increase performance. Rapid Spanning Tree introduces a proposal and agreement sequence to increase performance. If, for example, switch 1 is configured as the root switch with a priority of 4096, and this link came up between switch 3 and switch 1, switch 1 would send a BPDU to switch 3, but that BPDU contains a Rapid Spanning Tree extension which contains a proposal message. Switch 1 is proposing that it be the root. Now switch 3 in this case would send back an agreement message to indicate that it agrees that switch 1 is the root. Before doing that, it syncs its ports. Now if configured correctly, these ports should have been configured as edge ports. So in other words, they immediately go forwarding. In this case, when the proposal message is received, the edge ports will stay forwarding. So their state will remain at forwarding. However, all other ports that are not port FOST ports or edge ports go blocking. They are synced. In other words, this port is blocked. That prevents a possible loop. So once switch 3 receives that proposal from switch 1, it syncs all its ports. Edge ports remain forwarding. All other ports go blocking. As soon as that's been done, the switch sends back an agreement message to the root switch indicating that he agrees that the root switch is the root. As soon as that's happened, these ports go forwarding. This is the designated port and this is the root port in this topology. But notice please, this port is blocking to prevent loops. So at the moment, this is the designated port, this is the root port. These ports are forwarding. These ports are edge ports. They're forwarding. This port is blocking. Now at the same time, a proposal message is sent from switch 1 to switch 2. In this case, let's assume that the priority is 4096. The priority of this switch is 8192. In this case, switch 2 will sync all of its ports. So all of these ports will go blocking to try and prevent loops. The switch will send back an agreement message in answer to that proposal message. And the ports will go to the forwarding state. In other words, this is the designated port, and this is the root port. These ports are forwarding. Once that's happened, switch 2 will send proposal messages to the other switches to indicate that it's the designated switch. In other words, it's got the designated ports on those segments. So it'll send a proposal message to these switches proposing that it's the designated switch. They in turn will send back acceptance messages to switch 2. As soon as those messages are received, these ports can go to the forwarding state. In other words, these ports are designated ports. Remember, these switches at the edge will block their ports. So the result at the end of the day is very similar to what you would have with 802.1d, except it happens a lot quicker. Now, rapid spanning tree only has a single root. So in this topology, this switch is the root. The resulting topology is exactly the same as what we had with 802.1d. It just happened a lot quicker. Rapid spanning tree convergence will vary depending on the size of your topology, but with rapid spanning tree, your convergence, as a rule of thumb, is going to be between 2 and 4 seconds, whereas with 802.1d, it was around 30 seconds. So a massive performance increase. Rather than using timers, proposal and acceptance messages are used between the switches to increase the performance. There are also additional enhancements to rapid spanning tree, but we won't cover them here. The net result is rapid spanning tree is rapid. So that solves the speed issue in 802.1d and PVST. PVST has been enhanced to use rapid PVST. In other words, it's PVST with rapid enhancements. So a combination of rapid spanning tree and PVST can be used to increase performance and also to allow for load sharing across multiple uplinks. So once again, PVST would allow us to send some traffic across one uplink and other traffic across another uplink. And with rapid PVST, it makes the convergence a lot quicker. However, there are still problems with PVST, even if you're using rapid PVST. In a topology like this, we still have a root switch per VLAN. We still have an instance per VLAN, and we're still sending a BPDU per VLAN. On an interface like this, once again, 500 BPDUs are sent every 2 seconds, if 500 VLANs are permitted across that trunk. So the recommendation is to reduce the number of VLANs permitted on a trunk. If VLAN 10 and VLAN 20 are configured on switch 3, you would only allow VLAN 1, the management VLAN, VLAN 10 and VLAN 20 across these links. That will allow you to reduce the number of BPDUs sent across those links, and it also allows you to reduce the spanning tree size to increase performance. However, the industry developed another spanning tree version that gives you the ability to load share across multiple uplinks, but it allows you to reduce the number of BPDUs, it allows you to reduce the number of instances, and it allows you to reduce the number of root switches. And that protocol is multiple spanning tree. Multiple spanning tree provides multiple advantages. The first advantage is, rather than having a spanning tree instance and root per VLAN, you create individual instances. So in a topology like this, we would create multiple instances. So instance 1 and instance 2. And then we would map VLANs to those instances. So instance 1 would have VLAN 1, VLAN 10, VLAN 30, and VLAN 50 associated to it. Instance 2 would have VLANs 20, 40, and 60 associated to it. So our user VLANs as well as the management VLAN, are associated with the spanning tree instances. In this example, what we would then do is configure switch 1 to be the root for instance 1. Switch 2 would be the root for instance 2. The VLANs in turn are mapped to the instances, which means that user traffic from VLAN 10 can use this uplink, and user traffic from VLAN 20 can use this uplink. So we have the advantage of being able to use multiple uplinks. Just to reiterate, VLAN 10 is associated to instance 1. This switch is the root of instance 1, which means that this port is going to be the root port for that instance. Switch 2 is the root of instance 2. VLAN 20 is mapped to instance 2, which means this is going to be the root port for instance 2. So the first advantage is we can do load sharing where both uplinks are used. Different VLAN traffic is sent across different uplinks. But there are more advantages. Multiple spanning tree has rapid spanning tree built into it. In other words, it uses proposals and acceptances just like rapid spanning tree. That in turn means that multiple spanning tree is very rapid. Convergence is a lot quicker than PVST or 802.1d. In other words, multiple spanning tree incorporates rapid spanning tree and is thus rapid. What about instances, roots, and BPDUs? If this topology had 500 VLANs, PVST would have 500 roots. Multiple spanning tree, on the other hand, only has 3 roots. We made switch 1 the root for instance 1. We made switch 2 the root for instance 2. There's a built-in instance 0, called the internal spanning tree, which takes care of all the other VLANs that you haven't associated with instances. So 802.1q can support 4094 VLANs, so the remaining VLANs that you haven't associated are associated with instance 0. With PVST, we also had 500 instances. With multiple spanning tree, there are only 3 instances: instance 1, instance 2, and the IST, or instance 0. On the link between the 2 core switches, multiple spanning tree would send 500 BPDUs. Multiple spanning tree only sends 1 BPDU. So there are huge advantages to running multiple spanning tree in comparison to PVST. When configuring multiple spanning tree, you want to configure all of these devices to be in the same region. Now, a region is a grouping of switches that have the same region name. So that needs to be configured the same on all the switches. They need to have the same revision number, and they need to have the same instances. So you need to make sure that you configure the name, the revision number, and the instances the same on all switches if you want them to be part of the same region. It's good practice to ensure that your switches form a single region. But once again, there are multiple reasons to use multiple spanning tree. And an additional reason is that multiple spanning tree is an industry standard protocol. PVST is a Cisco proprietary protocol, but HP switches can run PVST and communicate with Cisco switches running PVST. The recommendation is to use multiple spanning tree and configure regions, and then allow for load sharing by creating different instances and making your first core switch the root for instance 1 and your second core switch the root for instance 2. That concludes this video discussing spanning tree. In this video, we looked at common spanning tree, PVST, rapid spanning tree, and multiple spanning tree. For more information, please go to hp.com/go/expert1.